The job application you submitted 3 weeks ago. You filled in every field, attached everything required, pressed the final button, and got the confirmation page and the automated email. Your application has been received. Then silence. You followed up a month later and they had no record of it. That experience, submission confirmed, data absent, is unsettling in a specific way. Not because the system failed in an obvious sense, but because the system said everything was fine. The confirmation was not a guess. Something, somewhere, decided to tell you the application arrived. And you discovered later that the information never reached anyone who could act on it. If you understand how reliable networks work, the confirmations, the retransmissions, the insistence that nothing is declared delivered until receipt is verified, this should produce a question worth sitting with. How does that happen? What does received actually mean in a reliable system if the application on the other end never saw the data? Think about pressing a buzzer at a block of flats. You find the right panel, locate the correct name, and press the button. You hear the buzz. The system works. The signal travels from your finger to a speaker inside a specific flat, where a light comes on and a noise sounds. The intercom has done its job. The signal arrived at the correct destination, intact, unambiguous. But whether anyone is home, whether they hear it, whether they press the entry button, whether they actually come to the door, none of that is in the intercom's contract. Its guarantee ended the moment the signal reached the flat. What the resident does with it is entirely outside its scope. You could be left standing outside, even though the intercom performed perfectly. Here is what that means for a network in one sentence. TCP's guarantee ends at delivery to the correct machine. What the software running on that machine does with the data after it arrives is a question TCP cannot answer. To understand where the boundary sits, you have to understand precisely where TCP delivers to. When TCP receives incoming data and confirms it, the bytes are placed into a buffer in the operating system's kernel, a region of memory managed by the operating system, not by the application. The application does not automatically receive the data at the moment it arrives. It has to ask for it. At some point, the application calls the operating system and says, "Give me what you have." The OS hands over what has accumulated in the buffer. Then the application reads it, parses it, validates it, and processes it. Every one of those steps is a separate opportunity for failure. The application might not have called for the data yet. It could be busy handling something else, in the middle of another operation, or temporarily paused. It might crash after receiving the bytes, but before writing them to a database. It might pass the incoming data incorrectly and discard it silently. It might receive the bytes, begin processing them, and fail partway through, leaving the user with a confirmation that reflects TCP's delivery guarantee, not the application's processing guarantee. TCP has no visibility into any of this. It delivered to the buffer. From where it sits, the job is done. The gap between bytes delivered to the buffer and application processed the request is not a design flaw in TCP. It is a structural property of how the network stack is divided. Each layer handles its own concerns and makes guarantees at its own level. TCP guarantees transport. Bytes arrive in order, without corruption, or the sender is told the connection failed. It cannot guarantee what happens above it, because it cannot observe what happens above it. The application is a black box from TCP's perspective. Data goes in. TCP has no mechanism for learning what comes out. This creates a category of failure that is invisible to the transport layer, an application that crashes mid-processing, a database that rolls back a transaction after receiving the data, a server that handles the same request twice because of how a connection was re-established. These are not network failures. They are application layer failures, and they happen precisely in the gap that TCP's guarantee was never designed to cover. The exactly once problem is one of the sharper illustrations of where this gap causes real trouble. TCP retransmits when it does not receive a confirmation. But confirmation of what? Confirmation that the bytes arrived in the OS buffer, not that the application processed them. If a connection breaks at exactly the wrong moment, after the receiving application has processed the data and committed it, but before the acknowledgement made it back to the sender will retransmit. The receiving machine sees fresh data arriving. The application may process it a second time. Preventing that from happening is not TCP's responsibility. It is the application's responsibility, using idempotency keys, transaction identifiers, database constraints that reject duplicate entries, or application-level acknowledgements that confirm not only receipt but completion of processing. These mechanisms exist because TCP's guarantee, precise as it is narrower than the guarantee most applications actually need. None of this is a criticism of how TCP was designed. The guarantee it makes is real, well-defined, and genuinely valuable. Bytes arrive in order, complete, or the sender is told the connection failed. That is a strong and useful promise. It is also a bounded one. The end-to-end principle, the design philosophy that shaped how the Internet's layers were divided, holds that lower layers should do reliably what they can observe and leave everything else to the layers above. TCP can observe whether bytes were transported correctly. It cannot observe whether the application was running when they arrived, whether it understood them, or whether it took the intended action. Asking TCP to guarantee those things would require giving it visibility into application behavior, which would make it not TCP, but something different and far more complicated. The implication is that whenever a system needs a stronger guarantee, confirmed action, exactly once processing, semantic correctness, it has to build that guarantee at the application layer on top of what TCP provides. HTTP response codes, transactional databases, message queues with their own acknowledgement protocols, idempotency tokens, all of these exist to close the gap that TCP leaves open, by design and for good reason. TCP's reliability guarantee is precise. Delivered means something specific. The bytes arrived at the correct machine, in order, without corruption. What it does not mean is that the application saw them, that the application processed them, that the intended action was taken, or that the meaning was understood and acted upon correctly. The buzzer worked. The signal reached the flat. Whether anyone came to the door is a different question entirely, and the answer to that question lives in a layer that TCP was never built to reach.